Obviously, we need to look at how past climates have changed. And there is a concept called climate sensitivity, which tells us how changing CO2 will affect the climate and what amount of warming may happen. For that, having past records is useful because it gives us a sense of how past variations in radiative forcing have changed the climate. So biogeochemistry techniques are used very commonly, and one of the most common ones, of course, is to use radioactive isotopes. So you have radioactive isotopes which splits into a stable daughter product and then continues to go on, and the total amount of the radioactive isotope keeps decaying, right? So you start with the parent isotope, which is radioactive here at let's say 24, and there is no daughter isotope when you begin. And as the parent isotope decays, the concentration of the daughter isotopes begins to increase, and that continues. And the point where they meet is one half-life, and then 2 half-lives, 3 half-lives, and so on. So depending on how long this half-life is of reducing the parent isotope to half its initial concentration, which means the daughter isotope reaches its concentration that's the same. So you go from 24 to 12, 0 to 12, and then 0 to 18 and 6 and 20, so on and so forth, right? So there are various radioactive isotopes. Not all of them are radioactive. There are also those that are just naturally existing as multiple isotopes of an element, like oxygen. For example, when we say H2O or oxygen, we always think about O16, O2 as O16, but actually H2O can have H2O16 or H2O18. Most of the oxygen in the atmosphere is, of course, O16, but there are tiny amounts of O18. There is also O17, which people are using these days, but let's just focus on O18 and O16. What are the processes? Basically, so the radioactive decay is a natural process. If you have an estimate of where you started, then you can age, let's say, a rock or a tree or ocean waters with these parent isotope by measuring how depleted it is from the original concentration or the natural concentration that you expect for that isotope. In this case, when water evaporates from the ocean, more of the O16 shown with these transparent drops will be picked up because they are lighter, so energetically it's easier to pick them up by the winds breaking the hydrogen bonds and so on. So fewer of the O18, H2O18 will be picked up, and which means more of the H2O18 will be left in the water than O16. If this process continues, then this O16 rich water will be moved in the circulation that we have been talking about towards higher latitudes, and when this clouds form and rain occurs, let's say in the ITCZ or in the storm track, for example, more of the O18 falls because it's heavier. So more O16 was picked up, but whatever O18 remains, more of it will fall in as rain. So the snow that reaches the continents, for example, has highly enriched O16, H2O16 in it, because less O18 was picked up, a lot of the O18 fell out as rain back on the ocean or on land, and very little of the O18 made it into snow. So glaciers over time would be depleted heavily in O18, which is measured here as delta O18, ratio of O18 to O16 in a standard sample stored somewhere, divided by O18 or O16, sorry, I said it wrong, O18 or O16 in the sample you're collecting somewhere, let's say in a glacier, divided by O18 or O16 of the standard that is stored somewhere, cancelled what I said before, minus 1 times 1000, which gives us in parts per thousand. So when we write zeros across this sloping dash, we call it percentage, but you add another zero, it becomes parts per thousand. These are so small that usually they are not measured in percentages but in parts per thousand. That's the simple idea. So if you go and look, for example, for some past evidence of climate in sediments, shells of the phytoplankton, or some other thing that is locked up O18, let's say a coral and so on, you can look at the relative depletion of O18 and try to see if it was a colder time, in which case a lot of the O16 would be locked up in glaciers, and the ocean waters that are imprinted on this paleoproxy, as they are called, would be showing more of O18. Okay, that's a very simple way that it works. So very useful if you know how to calibrate it and how to interpret and so on. So just as order of magnitude estimate, let's say you started with no depletion here. O18 by the time you reach the subtropics would be depleted by about 10 parts per thousand, and by the time you reach here in ice and glaciers, you would be depleted to the order of minus 20 to minus 40 parts per thousand. Okay, that tells you that there is a continuous depletion or deficit of O18 as you go to higher latitudes. The longer the water transport is, more O18 gets lost along the way with these processes. Okay, so ice sheets tend to be more negative O16, more negative O18, so they are O16 rich, and ocean will correspondingly get O18 rich in the source region because more of the O18 gets left behind. So considering ice ages take hundreds, 100,000 years to build, over the long periods you can imagine that you end up creating lots of such signatures. There are lots of isotopes, like lead, for example, has long half-life of I think 1 billion years, which allows you to look at the Earth history type of calculations, age of the rocks going all the way back to Archaea. There are other carbon isotopes which have a half-life of something like 8750 years, 8,750 years, which allow you to go back to 50,000 years in terms of measuring the depletions and so on. So one such evidence that we already looked at before is the Vostok Ice Core from Antarctica, and we have seen this before. Now it is shown together with the changes in insolation at 65 degrees north. So this is showing CO2 in parts per million by volume. 280 is the pre-industrial free atmosphere level. It went down, it goes down during ice ages and comes back up during deglaciation. Methane on this scale over here is in parts per billion, as we said. Well, sorry, this is the temperature, whereas the methane is shown here in the green line. So that's of the order of 700, and now it has gone over 1700 after industrial revolution and emission of methane from rice paddies, from coal burning, and so on and so forth. Okay. concentrations matter, and residence times will also matter, as we will see a little bit later on. So the idea of looking for insolation at 65 north is that that kind of sets the stage for whether snow that has fallen in 1 year will survive the winter, so that more snow can fall next year and it can get compressed and become glacier. If it melts, then obviously glacier mass will not accumulate, so it will begin to retreat. So 65 north is kind of the critical latitude which tends to determine this glacier accumulation or deglaciation. Obviously the southern hemisphere is different because of the Southern Ocean, but Antarctica has massive glaciers as well. Okay, so the asymmetry here comes basically because as you begin to cool, let's say radiation decreased at 65 north because of change in the obliquity or precession or ellipticity, which we'll see a little bit later on. Then as the albedo, let's say, increases by growing glaciers, more energy, more solar energy is reflected back to space, so it gets further colder. But as air gets colder, it holds less moisture, it gets drier, so the snowfall rates begin to decrease as glaciers grow in size. So the snowfall rates and the glacier growth rates begin to decrease, so it takes a very long time to grow glaciers. The snowfall rates become very minuscule. In fact, that's happening now on parts of Antarctica as well. It's complicated, as we will see a little bit later on. But when the melting happens, let's say for some reason the insolation increased at 65 north and slight melting of the glacier or the snowfall over winter started, then the albedo will decrease, more energy will be absorbed, it'll get warmer, then more snow will melt, the glacier will retreat more, albedo will further allow more energy to be absorbed. So this phase of melting goes relatively fast. These some evidence that in the recent deglaciation between 18 and 12,000 years ago had many hiccups on the order of 10 years or less. So rapid cooling and rapid melting happened on very short time scales. That's where this asymmetry comes from. So both are positive feedback. Here albedo is increasing, cooling is increasing, glacier is accumulating, but air is getting drier, snowfall rate is decreasing, but it's a positive feedback. Here glacier is melting, albedo is decreasing, and more energy is being absorbed, more glacier is melting. So this goes much more rapidly. Why do we worry about it? Because obviously right now we are in the melting phase. We are increasing greenhouse gases instead of solar radiation. So Greenland glacier, mountain glaciers, some parts of Antarctica are deglaciating, they're losing mass. CO2 is increasing, methane is increasing. This is now already more than 415 ppm by 2019. But you can see that the temperature is not increasing as fast as CO2. Why? Because a lot of the energy goes into the ocean or it goes into melting glaciers. So the atmosphere is still catching up. But the heat content of the ocean is increasing. So the total energy corresponds to similar feedbacks. Here, temperature leads by a little bit because the orbital changes change the insolation and increase energy coming in. And the CO2 and methane follow after some lag of few thousand years, because that depends on the coverage of the ocean and land vegetation and so on, wetlands, etc. Okay, so the phase lag here is that we are now increasing CO2 first and methane first, and then temperature is following, as opposed to here when temperature was leading and the greenhouse gases were following. Okay, that's the simple story of how we use paleo climate, how we do paleoclimate reconstructions. That's a bit long, but it's okay. The concepts are important, and you can make sure that you understood how we create past climate variability. Okay, the ice cores basically are glaciers basically trap the atmospheric signatures when the snow traps air bubbles and gets compressed, and a glacier forms. And glacier bubbles can be extracted, they can be dated to see how old they are, and then CO2 and methane can be measured to understand the composition of the atmosphere at the time. So you need dating and you need concentrations. The two things are involved. Okay, we'll see more about the glaciers. They are not like ice, they are like molasses. They flow because they are formed by this compression of snow and not necessarily by directly freezing water into ice.